Okay, let's jump right in. Welcome back to The Explainer. Today, we're basically embarking on a cosmic detective story. We are going to journey out to the absolute edges of the observable universe to track down the most energetic, chaotic, and honestly, terrifyingly powerful objects in existence. We're going to demystify quasars. To kick off our investigation, I want to hook you with a physical paradox that literally baffled astronomers for decades. Think about this. How can a single, relatively compact object completely outshine an entire galaxy made up of hundreds of billions of stars? I mean, on paper, it sounds completely impossible, right? To give you a real sense of the mind-bending scale we're dealing with today, consider the number 500 trillion suns. Just recently, astronomers analyzed a quasar known as JO 529 4351, and they discovered that it shines with the intensity of 500 trillion suns. It is so luminous, it's actually 20,000 times brighter than our entire Milky Way galaxy. To understand how something this insanely bright can even exist, we kind of need to travel back in time a bit. Act 1. The Anomaly. This whole mystery actually started without optical telescopes at all. Back in the 1950s and 60s, right after World War II, there was a massive boom in radio astronomy, and these early radio telescopes started picking up really strong, localized radio signals coming from deep space. But when astronomers finally pointed their traditional optical telescopes at those exact locations, all they saw were what looked like ordinary, faint blue stars. The problem? Normal stars just don't pump out radio waves like that. This became known as the radio star mystery. They looked like stars, but they were behaving completely differently. The contrast between what we already knew and what we were suddenly discovering was just stark. In a normal, ordinary galaxy, most of the light comes directly from stars, so it peaks at visible wavelengths. But these new objects, these so-called active galaxies, were totally different. The vast majority of their light was coming from gas, peaking at radio and X-ray wavelengths. And they had a central nucleus that was inexplicably incredibly luminous. And the mystery only deepened once astronomers actually broke down their light spectra. They found these bizarre, really broad emission lines that completely defied all known stellar physics at the time. The spectra just did not match any typical stellar elements. The scientific community was completely stumped. They literally had no idea what they were looking at. Act 2, the breakthrough. This is the moment the puzzle pieces finally clicked together and completely altered our understanding of the cosmos. So let's walk through this incredibly rapid sequence of events. In 1959, the third Cambridge catalog mapped out a bunch of these strange radio sources, but the resolution was pretty bad. Then, in 1962, a brilliant astronomer named Cyril Hazard tried a technique called lunar occultation. Using the Parkes radio telescope, he literally waited for the moon to pass directly in front of one specific source, called 3C273. By timing exactly when the signal vanished behind the moon and when it reappeared, he pinpointed its exact location. And that allowed astronomer Martin Schmidt, the very next year, in 1963, to aim the massive 200-inch Hale telescope right at it and get a crystal clear spectrum. And boom, this is where the light bulb finally goes on. Schmidt realized those bizarre, unrecognizable spectral lines weren't some unknown alien element. They were just ordinary hydrogen. But they were shifted massively to the red end of the spectrum by 15.8%. Now, in astronomy, a red shift like that means an object is moving away from us very, very fast. 3C273 was receding at a staggering 47,000 kilometers per second, which meant it wasn't a local star in our galaxy at all. It was 2.4 billion light-years away. So the absolutely crucial takeaway here is this. If something looks like a relatively bright star in our night sky, but it's actually billions of light years away, its true brightness must be beyond human comprehension. 3C273 was outshining its entire host galaxy by more than 16 times over. Because they look like stars but definitely weren't, they were dubbed quasi-stellar radio sources, which thankfully was pretty quickly shortened to just quasars. Act 3, the central engine. So, the big question now is, what kind of physical engine could possibly generate this apocalyptic amount of power, all from a space barely the size of our solar system? Well, let's use a bit of process of elimination. Could it be a super dense cluster of stars? Nope. To pack that much light into a space that small, the stars would have to be so close together they'd be gravitationally unstable and just collapse. Okay, what about supernova? Exploding stars. Well, to maintain that continuous, insane brightness, you'd need multiple supernovae going off every single year, indefinitely. Totally impossible to sustain. There was really only one suspect left that fit the physics, a supermassive black hole. Now, a black hole itself obviously emits no light, right? Its gravity is too strong. The light is actually coming from what surrounds it, the accretion disk. Picture a swirling maelstrom of gas and matter. As the black hole's immense gravity pulls all this material inward, it spirals faster and faster. All that gas rubs together at near light speed, which generates unimaginable friction and heat. We're talking tens of millions of degrees, blazing with electromagnetic radiation across the entire spectrum. And if you compare the energy efficiency, it reveals exactly why quasars are the brightest things in the universe. Look, when a star like our sun fuses hydrogen, it converts about 0.7% of that mass into energy. Not bad. But dropping matter into a spinning black hole, that accretion process can convert up to 40% of the mass directly into energy. It is exponentially more efficient than nuclear fusion. It's quite literally the most efficient power source known in the universe, short of matter-antimatter annihilation. So the sheer anatomy of this engine is staggering. We are talking about central black holes weighing millions, sometimes billions of times the mass of our sun. As matter falls in, extreme X-rays and ultraviolet light just blasts outward. And sometimes the intense magnetic fields twist up and snap, launching massive relativistic jets of plasma deep into intergalactic space. In fact, the Hubble Space Telescope actually captured an image of a visible jet shooting out of 3C273 that is 200,000 light-years long. Act 4, Cosmic Sculptors. Let's zoom out and see how this all fits into the grand scale of the cosmos. Because as we now realize, quasars aren't just bright lights, they are cosmic sculptors. Because quasars are so incredibly bright, their light can travel billions of light-years before finally reaching our telescopes. And this means they act as literal cosmic time machines. When we observe a really distant quasar, we aren't seeing it as it is today. We are looking directly back in time at the dawn of the universe. We're seeing the environment exactly as it was when the cosmos was just a newborn. And honestly, what we're finding back there is shocking. Take the quasar J0313-1806, for example. We see it as it existed just 670 million years after the Big Bang. That's a blink of an eye in cosmic terms. Yet even at this incredibly early stage, its black hole was already 1.6 billion times the mass of our sun. And it has a ferocious diet, devouring the equivalent of 25 entire suns every single year. Just for some context, the black hole in the center of our Milky Way is mostly dormant, but this ancient behemoth was growing at a terrifying runaway pace. Now, this kind of aggressive growth has massive consequences for the galaxy living around it through a process we call AGN feedback. Basically, when the quasar ignites, the intense radiation and relativistic winds blast outward like a giant cosmic blowtorch. This sheer, overwhelming force literally sweeps the cold gas right out of the host galaxy. And since cold gas is the raw material you need to birth new stars, star formation just stops. The quasar effectively kills the galaxy's ability to grow, a process astronomers somewhat dramatically refer to as quenching. But all of this leaves us with a really massive unsolved mystery. How on Earth do these supermassive black holes grow to be billions of solar masses so quickly after the Big Bang? Theoretical models say they simply shouldn't have had enough time. Scientists suspect it has something to do with super-Eddington accretion, which is basically breaking the universal speed limits of growth. It was likely nurtured by the incredibly dense, chaotic gas environments of the early universe that allowed for these runaway collisions. But exactly how it happened, that is still fiercely debated today. And that is exactly why the hunt continues right now. Our modern observatories act as the ultimate cosmic detectives in this ongoing case. The Subaru telescope, for instance, has been crucial in discovering hundreds of these really faint ancient quasars. The new Euclid Space Telescope is actively peering into the first billion years of the universe to uncover more of these primordial beasts. And of course, Hubble continues to track those massive galactic-scale jets so we can better understand how they interact with their surrounding environments. I want to bring this whole crazy cosmic scale back down to Earth for just a moment with this quote from astronomy researcher Christian Wolff. He notes, "What makes the black hole visible to scientists is the growth that devours everything around it." It's a pretty profound thought when you step back and think about it. We can only witness these magnificent cosmic lighthouses because of their ravenous, destructive appetite. We only see them because they are literally tearing their immediate surroundings apart. Which leaves us with this final, lingering question to ponder today. If these magnificent, terrifying engines have been out there shining away since the very dawn of time, what other massive secrets are still hiding in the dark ages of the early universe, just waiting for their light to finally reach us? Thank you so much for joining me on this explainer, and as always, keep looking up.